Good afternoon, everyone. Thank you for joining our release webinar. Today, with my colleague Denis Ferreira, Milad Bibordiani, and Tanvir Rahman, we are very happy and proud to present some of the numerous announcements and updates that have been done in Diana 11. For the ones that are not familiar with our webinars, I just want to briefly mention that during the session, your microphone will remain muted to avoid any background noise disturbance. This webinar will be recorded and available on our YouTube channel within 1 or 2 days after today. There is a chat box where eventually you can ask questions. So at the end of the session, I will have a look, monitor the questions, and see some of the questions are relevant for the whole audience. I will address them. Otherwise, we will get back to you per email for more specific questions. So having said that, let's start this webinar. And before to move to the, let's say, the new features introduced in Diana, let's first have a short introduction about our company, something relatively short, and about the capability of our software, because some of you might be new to Diana. So before we present the new announcement in terms of modeling features, material models, analysis and results and documentation, let's give you some input about our company and Diana itself. So Diana is a short form of displacement analyzer and is a general finite element program which is dedicated to all type of civil structure, can be bridge or infrastructure, but also to geotechnical and petroleum engineering application. Our aim is to provide a range of efficient engineering solutions to the daily or specific types of engineering problems that, by increasing the accuracy of the final results, our clients could optimize the cost of their project, because at the end, it's always about money. Our core value in our company are presented on these slides and can be summarized in 3 words: reliable, collaborative, and solution-oriented, which is actually 4 words. So reliable, so we work to build an innovative state-of-the-art software, providing our user with consistent and reliable results. Collaborative, we create a collaborative and engaging work environment that stimulates teamwork and also contribute to personal development, which is very important. And solution-oriented, having a proactive mindset to solve clients' questions as well as challenging engineering problems within the Diana software. So this is really the essence or the core value in our company, Diana. Let's now quickly go through the main applications that are listed there. And I will just give you in few words what are the main aspects before to move to the new features that have been introduced to our new Diana version. So we start with geotechnical and tunneling. We have a very good integrated solutions for all type of geotechnical and tunneling applications. So you can use the integrated environment of Diana for any type of tunneling and underground structures. For ground freezing, also called 3-phase analysis, we have a solution. For real soil structure interaction, we also have a good solution. So if you have some sort of interaction between the underground and the surrounding soil or rock, you can model it with the concept of nonlinear interface behavior. Coupled groundwater flow stress analysis is also part of our solution, slow stability, and many more. Next to that, we have a very comprehensive solution associated to reinforced concrete and early edge behavior of the concrete. That's mainly when the casted concrete goes through the process of hydration. And this is available for any type of concrete box girder or composite structure. For dam structure, it's also very important because of the process of casting, curing, hydration, and impounding. We have also a good coverage for the design check, including the reinforcement based on the Eurocode, mobile load and design load generator, and indeed the cross-section design check. You can use it in conjunction with your bridge applications or your general structural analysis application. We have different solutions in order to give you a good estimation about nonlinear response of the model without entering into the nonlinear detail parameters input and setup each iteration. It's called the sequential analysis. Temperature and stress coupling let you analyze how the concrete goes through aging. Cooling pipes is also another powerful feature that we offer in both 2D and 3D in order to control the hydration process. Crack initiation and propagation in concrete, one of the powerful features in Diana. And also fire effect, how the fire could affect durability of the structure. Among other applications, we can refer to the masonry and historical construction. In Diana, we offer different solutions at meso or macro levels. You can use Diana to model the interaction between the individual brick and the mortar joints. For dams and dikes, Diana offers the solution. It covers all the aspects of construction for all types of dam structure. You can consider the fluid structure interaction, dynamic effect, and also induce damage to the structure. Fire analysis is another area that, based on its importance these days, has become one of the main topics for structural checks. And again, Diana can be considered as one of the most reliable solutions for that. For earthquake analysis, you can of course use Diana for general dynamics or seismic analysis. Among the advanced type of application, Diana is very well known as well in the field of oil and gas and nuclear structures. Based on the type of complexity, you can stimulate 3D geomechanical depletion or borehole stability, for instance. For nuclear structures, you can analyze concrete containments or underground waste storage. So as you can see, I mean, Diana offer quite a wide range of application and solution. So after this quick and short introduction, let's now go through the new features and enhancements that are available in our new release version Diana 11, which is a major release, because there's quite a number of new features and enhancements. And let's start with the enhanced and intelligent connection algorithm for complex model interaction. For the ones that are familiar in Diana, in previous Diana version, there was only one algorithm for the connection. And the concept used there was the following. When no connection is defined explicitly, all coincident topology is automatically connected. So far, no complexity. When a connection is defined explicitly between shapes or between a shape and its surrounding, all coincident topology that is neither part of the source or the target is disconnected, and the selected connection type is created between the source and the target. Therefore, it may be necessary to reunite coincident topology that is either part of the source or the target of the connection, but are not part of the connection itself. As a result, and people who have been dealing with the modeling of interface understand what I'm saying, the creation of interfaces introduce coincident nodes across the interface, which share the same coordinate but belongs to different elements across the interface. And when there is a geometry boundary touching either side of the interface, the node is split at the intersection, which is not desired for most of the cases. So for the one who have been dealing with complex model with interface, I'm sure that they have run into this problem of splitting nodes. But the good news is that Diana 11 has a new connection algorithm created to solve problems of disconnected part of the models after creation of the interface. And the concept of this new algorithm is as follows. So when there's no connection defined explicitly, all coincident topology is automatically connected. So same as before, no change compared to previous version. Then when a connection is defined explicitly between shapes or between a shape and its surrounding, the nodes at the coincident geometry will be duplicated and the selected connection type is created between the source and the target. Good to know that both algorithms, the old one and the new one, coexist in Diana 11, and the user can decide which of this algorithm he can use in the creation of the connection. To change the behavior to the new connection algorithm, you just need to go to the main menu, connection, and under connection preferences, you can select advanced options in the connection solver parameter, in the connection solver mode parameter. The connection solver mode parameter is a new parameter offered in Diana 11 with a couple of options. The off options basically do not merge any nodes. That's what you can see here. The legacy, so that's basically the algorithm from version 10.10 and earlier, remain accessible in the program and can be activated by selecting this option. It means that it will disable the solver and the default behavior of the connection is activated. So this option is only there for backward compatibility with your model. The basic option behave as the old options, but using a different algorithm. So this option is the default in Diana. And this algorithm opens all coincident nodes if there is a connection defined in the intermediate surrounding area. So basically, you end up in this situation. Finally, the advanced option, which is a new one, enables the main feature of the connection algorithm solver. So the advanced connection algorithm aims to resolve node connectivity based on the topology and coincident information of the shape geometry. And additionally, this algorithm identifies the connectivity issue and report them as overdefined or underdefined scenario. So this is basically these options that you can select under your preferences. And you see that there are a couple of options that I'm going to highlight in the next slide. So to elaborate a bit more on these enhancements, let's look at the following examples where we can see the behavior of the advanced connection solver model mode in comparison to the basic connection solver mode. So in the basic mode, which is the one described here, the node that is common to the three shapes is disconnected after the creation of the interface, resulting in 3 nodes in that location. So the horizontal shape, I mean this one, is not disconnected, resulting in 2 nodes in that location, which is the intended behavior of this basic mode. The new algorithm, the so-called advanced, is able to solve the discontinuity that appeared mostly in modeling dams, such as joints and foundation, or concrete joint structures and tunnels, while maintaining good backward compatibility. In geometry levels, the new advanced connection algorithm solves the problem of disconnection for geometry with the same dimension. So the enhancement is general, and this applies to most of the cases. And you can see here the outcome when you check, for instance, for the resolve conflicting connection by opening, or using the option use element class to restrict connection. So this is a major enhancement, and people using Diana already for a while who have been modeling dams, for instance, knows that the old algorithm had some shortcomings. So this is really a major breakthrough regarding the definition of connection in complex model in Diana. Next to that, we have also introduced an interactive arbitrary beam cross-section editor. In previous Diana version, it was possible to define cross-section for beam elements with arbitrary shapes, but it was only possible in the DAT file, which is basically the text file with all the model input. So by means of manual editing, basically. And we can agree that in terms of user friendliness, it was not a must. So in Diana 11, it's now possible to do it interactively in the Diana interactive environment. In the cross-section definition type of the edit geometry widget. So in addition to the predefined profiles that were already there, there is now the new option of arbitrary shapes that you can find under the cross-section definition type. And for this, you have 2 forms, the arbitrary, which is the one on the left, and the symmetry, where basically you just define some of the corner points, and using a symmetry, it built the cross-section of your beam. So this is also, in terms of user-friendliness, a plus when coming to the definition of arbitrary beam cross-section. Another major enhancement is the advanced mesh quality assessment. In previous Diana versions, only mesh quality information that was available was prior to running an analysis. Diana was checking the mesh quality based on the smallest angle of each element and issue a warning in the Windows message dialog box of Diana IE. Diana 11 presents new features in relation to calculation and visualization of the mesh quality metrics. And there are now 6 methods for the calculation of the mesh quality. You have the element measure, which basically measures the length of the element in 1D or the area in 2D and volume for 3D. You have the minimum angle, the aspect ratio that measures the ratio between the longest and shortest edge length of your elements. You have the distortion ratio, you have the skew, and the scale Jacobian. And to see the graphic representation of the mesh quality matrix in Diana, you need to go to the main menu under Mesh and color element by mesh quality metric color. The mesh quality matrix settings are under the properties, as most of the property definition. And under the property, under the mesh quality matrix, you basically find the settings for the control plot of the mesh quality. So you can play with the color scale limit, the bounded colors, the title and legend appearance, same as other control plot in Diana. So this is also a major enhancement when it comes to analyze and review your mesh quality. So this is it for my part, and I'm going to invite my colleague Milad to take over the presentation and to continue presenting the enhancement introduced in Diana 11. Milad, it's your turn.
Yes, good day to all. Can you go to next slide, please? Yeah, thanks. For this release, we have extensively worked on performance of Diana. One of the main improvements was related to pre-processing of composed elements. After multiple code optimizations and also using more advanced algorithms in defining the relation between composed and continuum elements, Diana 11 can pre-process orders of magnitude faster than previous version. For example, here you have a model that in the most fine mesh has 2.5 million continuum elements and 50,000 composed surfaces. And for this case, as you can see, the preprocessor runs almost 30 times faster. Can you go to the next slide, please? Here is another example where a phased analysis is done with composed lines in this case to obtain internal forces in tunnel linings. And considering that the preprocessor runs, in this case, 100 times faster, the total analysis time is reduced by half. And please note that all these performance gains are amplified limitlessly as the mesh becomes finer. Next slide, please. Another performance improvement is related to space functions. When there were large space functions with fine grids for different things such as material properties or loads, runtime would increase quite significantly in previous versions. In Diana 11, a new state-of-the-art high-performance data structure is developed and implemented that can address such bottlenecks. And in this example, where the grid had 700,000 points, Diana 11 runs more than 9 times faster than the previous version. The next one, please. In Diana 11, we have worked on the mass properties of groundwater. Previously, this was not considered. The mass of the groundwater was not considered in nonlinear time history analysis. Only the weight of the water was considered. And now, depending on the physics of the model, user can choose to calculate water mass once at the beginning and include it in the mass matrix, or if it is expected that the changes in groundwater during the time history analysis are considerable, then the calculation and update of the mass matrix can also be done in every time step. These settings are available in transient, yes. In the transient setting, in the nonlinear structural analysis, as you can see on the left side. And here I have shown a hypothetical example where the groundwater is rapidly drained out of the domain, while it is also subjected to a sinusoidal base excitation. The base reaction is reported in the right figure for three options. One is completely ignoring the mass of the water in the domain, and the other one is only calculating it once at the beginning, and the last option is to calculate and update the mass matrix at every step. And you can see from the results that the orange and green lines shows the models without water mass and with mass only calculated once at the beginning. But considering that in this case water level change is significant, blue line represents the most accurate result, where it starts similar to the model with water and then gradually converges to the dry model results. Can you go to the next slide, please? Another improvement was related to free field elements. Free field elements are used to model unbounded soil domain with truncated regions. These elements provide equilibrium forces and also radiation conditions. In DIANA 11, all nonlinear material models can now be assigned to them. Well, this process is internal, but previously only a few simplified soil models were available for free fills. This new addition provides a lot of flexibility in modeling the soil domain. And here I'm showing just an example case for the contours of lateral deformation using in one model free field and in the other model only tying. And this comparison, where a rectangle domain with a structured mesh is used, the comparison shows good agreement between the results, which verifies the accuracy, but please note that the capabilities of free fields are beyond this case. For example, when there are arbitrary geometries or when wave radiation plays an important role, then we have to use free field and tying is not sufficient. Well, this is what is related to my part, and I will ask Tanvir to continue with the rest of the presentation. Thanks.
Thank you, Milad, and good afternoon, everybody. So the first item that I'm going to present is about adding new elements to deformed position in phased analysis. Generally, if we add new elements on top of existing elements, then only the nodes that are common gets the deformed position, but the other nodes of the new elements are in its original position. That makes the deformation pattern quite strange. To solve this, we also in the past DIANA versions we had something called deform import load, but it could solve the problem, but it was very cumbersome to define and apply it. In DIANA 11, we have made it fully automated. Like you see, we have a checkbox for it, and then yeah, that's all. Then then deform import load will be generated internally, and also the necessary support, everything will be generated internally. And on the right side, we see a comparison like with and without doing it. On top, we see if we don't do this deform import treatment, then we have discontinuity in the displacement field, while in the lower picture we see the deformation pattern is as expected. Next slide, please. This is about local convergence check. Generally, in any finite element package, always global convergence check is made. But then what happens sometimes is that globally a model appears to be converged, but there are local inequilibrium present. And that requires a need for enforcing local convergence in certain part of the model. Also, it may be used in another way, like sometimes it is possible a model is converged, is not converged globally, but the region of interest for the user has well converged. And then user can only select that part and then go on with the analysis. Please note that even if we enforce local convergence, then the analysis will proceed based on the convergence on that local domain. But Diana also computes the global convergence and for the rest of the model that we call, say, the complementary part. So those convergence computations are also done. It is just not used for the decision making of going to the next step, but that state is presented in out file, and also there are separate output item for that. So even if somebody is relying on local convergence, one can check always what is happening with the global convergence. On the right side, we have an example or have an application of it, and it is about strength reduction analysis for slope stability. Here, the model is quite big compared to the slope, which is marked by red. Here, what happens is that the model converges quite easily because the large part is outside the slope, and then it shows a higher factor of safety than it should be. Like if we only model the red part, it will show a lower factor of safety. Like if we model the whole part, it will show in this case 1.8 as the factor of safety. If we model only the red part, it will show something like 1.7. But with the possibility of local convergence check, what we can do is that we can still model the whole part, the big model, but enforce the convergence check only, say, on the red part. Then we end up to something like 1.68, which is very close to what we get if we model only the small part, which gave us like 1.7. It is just an application. Next slide, please. Yeah. It is for heat flow analysis with cooling pipes. In Diana, cooling pipes are 1D elements, and then the problem is, in reality, cooling pipe has a certain radius, and heat transfer happens through the cylindrical surface. In a 1D element, that cannot be reproduced exactly. So as a remedy, what we have done is that in a region same as the radius of the cooling pipe, we make that region highly conductive. Then it can reproduce more or less the same effect as when if we can explicitly model a cooling pipe. In the picture on the right side, we have tried to make such a comparison. So the top picture, which we call as reference, is we have not used any cooling pipe here, but really modeled it as a as a steel pipe and give similar convective properties on the inner side, and then we see it has certain temperature pattern. And in the next picture, just the below, we just simply used cooling pipe as we always do, and then we see the temperature profile is not really matching very well. And in the last one, when we give a high conductivity zone around its radius range, then we see the temperature pattern is matching quite well with the reference. Next slide, please. Yeah, this is a similar concept, but in structural sense. It is about pile tip. At pile tip, we have typically a point interface element for the interaction with soil, but then pile also has a finite dimension, and while in our modeling, it is modeled as a beam element, so it is a point connection. To simulate really the geometry of the pile, what we have done is that around the pile tip, we make a zone of continuum element elastic and gave them same stiffness as the stiffness of the pile. Then, even though the pile is modeled with beam element, it acts more like a volume pile, and then the interaction happens through more nodes. And now, if we compare the left to right picture, we see the deformation around the pile tip is much smoother than when we don't do it. Next slide, please. Yes, it is about connection for frame structures. We can have, for beam and shell elements, we can have hinge connection or slide connection. We had this possibility also in the previous Diana versions, but then what was done internally is that it was fully disconnected first, and then the appropriate doves were tied, and in that way we could achieve hinge or slide. The problem of that method is that if we have, say, too many beams or shells connected, let us say too many beams connected at a point, and then the tying condition becomes too complex, and sometimes we run into tying errors. And also, because it is more like a nodal approach, then if one node is we call as hinge, then the whole connections all becomes hinge. Like, even if let us say if we have 3 beams connecting in one point, then all 3 will become hinged. And now we have another approach, which is not based on disconnecting the nodes or then tying it back again. What we do, we internally duplicate, say, the rotational dove for hinged connection. Then we don't need any tyings, and then it is more an element-based approach than node-based approach, and then we can more precisely define hinge or slide. Like if we come back to the example of, say, 3 beams connecting at one point, then we can make 2 of them hinged, but not the other one. So it gives more freedom, and it is simplified. Please note that this feature was actually present in Diana kernel for many years, but it was not available through Diana IE interactive environment. Now we made some improvements and made it available through our graphical user interface. Next slide, please. This is about bond slip reinforcement through gap. So we may have situations like, say, tendons in box girder bridge, like, and we may have gap in between, but in the past Dyna versions, if we define a bond slip reinforcement, then in the gap, the reinforcement becomes disconnected. We could treat it also in the past, but then in the gap, we had to define a gap interface or dummy elements. So there has to be some elements to make the interface, to make the continuity of reinforcement possible. But now, even if there is nothing in the gap, Dyna will generate just a beam or truss, let us say truss, because that is more suitable for tendons. Then the tendon remains continuous. Next slide, please. Now we come to constitutive models. In Dyna 11, we have a new rate-dependent concrete damage plasticity model, and it is quite robust, very suitable for dynamic analysis, and it has some nice features like, yes, as the name suggests, it has scalar damage parameters, it has plasticity in compressive part, it confinement effect is naturally incorporated in the model, and it is strain rate dependent, so it is sensitive to loading rate, and the formulation is thermodynamically consistent, efficient. So this is a nice addition to Dyna 11. Next slide. Yeah, now it is an example of this model. We applied it in a large dam structure, and we did earthquake analysis on it, and we see at a later step how the damage propagated. Next slide. Yes, it is another improvement on bond slip on bond slip behavior. In the past, you may see here that in the backbone curve, and also in some part of the cyclic behavior, there is a plateau-like situation. And particularly in load control type situation, which is very common when it is for earthquake dynamic analysis, it may end up to very large displacements when it is on the plateau. So in Dyna 11, we have added a new parameter, which is a factor on the initial shear stiffness of the bond slip interface. Then one can give some slope on the plateau, and then it becomes much more stable. Next slide, please. Yeah, it is Denis's turn now. Thank you.
Thank you, Tanvir. Good afternoon, all. Continuing with the new features for constitutive models, the Dyna 11 presents an update of some major model codes. Here we have the FIB model code 2020. That is a new material model, and the previous version, so the FIB model code 2010, is maintained. For the error code, error code 2, there is a new parameter for the version that you will see inside the widget of the error code material model. So here you can select the version 2004 that was previously available, and the new version for 2023. Next slide, please. Also, for there are also updates regarding the model codes used as curves in the total strain crack model. So we have a tensile curve from the FIB model code 2020, and also in the tensile curve for the FIB fiber reinforced concrete, we have the option now for FIB model code 2020 based. Also for the compressive curve, there's the option for the FIB model code 2020. Next, please. In terms of the total strain crack model, but for fire design, and still related with the update of the model codes, we have the compressive behavior. So we have for a new fire design curve from Eurocode 2, version 2023. And there is also, if you see at the bottom of this widget, there's also the corresponding option for the recovery of strength when cooling down. And here you also see the updated Eurocode 2. There is a new parameter that you see in the middle of this widget that is field temperature dependent values of parameters according to the model code. And when you select this option, the diagrams, all these diagrams that appear below, so the tensile, the temperature compressive strength, the temperature strain at maximum compressive strength, and the temperature ultimate compressive strain, so they appear and they are automatically filled in according to the Eurocode. All this is only available when you select the aspect for thermal effects. Next, please. So now I move to the part of the analysis progress and results visualization. And I start by presenting the restart analysis in Diana. So in previous Diana versions, it was already possible to restart a nonlinear analysis from a given step. For example, when we had a non-converged step that we could resume the analysis from there. However, that process was not very user-friendly, not very direct. And now in Diana 11, we offer this possibility in a nicer manner. So you will find this under the settings for load steps or for time steps or start step analysis. You will see there is these options of save conditions. And under the save conditions, there are the options of saving at user defined. So you select a step that you want to save the data from the analysis. It can be the option of all, so you save all the steps, of course, with a large amount of data being saved. You can also choose for the last converged and the last executed steps. Diana will then save the corresponding data file in order to be able to restore an analysis from this selected step. Next slide. So yes, so in this next slide, I point out for the restore. So you can restart an analysis from a given step, and here is the command to do so. Is the restore command, in which you can define step number you want to restart an analysis. There is also a new tutorial that exemplifies how this is done now through Diana IE. Next slide, please. In terms of the analysis progress overview, so this panel that Diana users got used to see it when we ran our analysis, it is now in Diana 11 redesigned and enhanced, so you will definitely see it very differently. So it provides now more information about the development of the analysis. So there's a clearer view of the analysis stages and the behavior during the runtime. And also a great novelty is that you can save and restore the data, right? So this data was sometimes very, very nice to have, and it was lost when we finished the analysis, and now we can save and load and have it back, all this information. So we have an enhanced convergence overview with a pie and scatter charts showing the solver performance with information also about the convergence behavior. So we have now these graphs for the norms. We also have here in the middle, if you can see, there's some information about the crack and plasticity monitoring chart, so visually displaying the damage while the analysis is running. Next slide, please. In terms of results visualization, it is now possible in the ANA 11 to visualize the animated deformation of an eigenmode in an oscillating manner. For this, you will see a new icon, this new icon that appears here, in the animation toolbar. And when you click in this icon, you activate this oscillation view. And there are some looping options that you will have under the animation properties. So you can run until the end, so for only one loop, or you can rerun from start for continuous looping animations. Next, please. Now, in relation to probe curves, there is a new option to see the extreme values, so minimum and maximum, or only minimum or only maximum. And you can activate these under results properties, probing curve settings, and with the name, so you have this new parameter that is called enable extreme values for probes, and extremes to show, where you select which extremes you want to show. Then when you are inside each probe curve, you can select the show probe extremes. So you can have several probe curves defined, and then only showing maximums or minimums in selected ones. Next, please. Continuing with the contour, the probe curve, there is also a new option for seeing this probe curve with the color scaling. So you also find this option under the probing curve settings, and the name is contour coloring probe curve. So when this option is active, the probe curve is displayed with the same color code as the contour plot. So with the same legend as we see in the general contour plot. And next, please. So now I move to the new features related with automated workflow. We have this new add-on feature that allows users to extend the ANA-IE with customized Python scripts. So these add-ons that are programmed with this Python script can automate repetitive tasks or perform group commands, and also generate interactive widgets in the interface. So what we see here in the right, this beamline, this is something that was created through Python and added to the ANA. So you can create your own widgets in the ANA. You see here this add-on preference menu. So this is a new section in the main menu that is called add-ons, where you will find this add-ons preferences. Here you can load your macros and see some information about it. Then these loaded macros or these loaded add-ons will appear in the main menu under the add-ons section, and they are ready to be executed. So this is a quite a new feature in Diana. So for this reason, we have a new section in how this works, and also we have a new tutorial with an example, so explaining in detail how you can use this feature to optimize your own workflow with Diana. Next, please. So I finalized with this feature that is a general improvement of the report generation. So Diana has this automated report generator, and the workflow has been enhanced. So now it presents clearer titles and also a nested structure for adding sections in a report in a way that you will find your the parts of your model that you want to include in the report in a nicer and faster manner. There are also a good number of items, as we see here in this list, that were not possible to be added in previous Diana versions, and now they can be included in this automated report. We are talking about items that are both from geometry and mesh levels. So I conclude with this on my side, and I pass the word to Jean-Claude. Thank you.
Thank you very much, Denise, and also to Milat and Tanvir for covering all the improvement and enhancement and new features introduced in this major release, which is Diana 11. As you may already know, if you are registered to our newsletter, this version is available since mid-December. So if you have a valid subscription, you can download it, use it, and challenge it. We would be more than happy to hear your feedback and first impression. So having said that, it's important that you make sure that you are registered to our newsletter. This way you can get the latest news about Diana and our company, and also the list of our upcoming events. There are upcoming webinars in February, and also online courses coming in March. So please register to our newsletter to keep an eye on our activities, I would say. I quickly checked the chat box. I saw one or two remarks that we will address per email because we are running out of time now. So don't worry, we will get back to you. I'd like to thank you all. There was quite a large audience today for this release webinar, so a lot of interest. We are very happy with that. So I'd like to thank you on behalf of Diana. And one more time, I would like to thank my colleague Denise, Milat, and Tanvir for taking the time to cover some of the new enhancements or features of Diana 11. So I thank you all, and I wish you a pleasant end of the day or pleasant end of the morning, depending where you are located in the world. And I'm sure that we will be in touch in one of our upcoming events. Thank you all. Bye.